Okay, hello. It's like 1 minute before 8. Oh, and this is kind of meta because currently you're looking at me watching a clip that I just recorded where I was testing how the Twitch stream was working. So let's make it a little less meta and a little more chemistry. Of course, this is just Gen Chem, but any OChem, meta does actually have a chemistry meaning. And since I'm technically 1 minute before the beginning of the stream, I'm just going to show you that you're talking about a benzene ring, and you have a thing here called thing A. Then this spot and this spot are called ortho spots. Those are the ortho positions. This is the para, and right here and here are our meta positions. This was benzene, right? So anyhow, that's not Gen Chem stuff, but that is a reference to how even chemistry has some meta to it. Okay, now I am seeing officially 8 o'clock, so let's dive right in. I was just working through this in a practice sense, as usual, but I'm going to go ahead and clear out my practice so we can do it together. We being you, hello you, watching this video at this time. I hope that things are going well and that you are having fun with chemistry. You probably have an exam or some homework, or maybe you're just super curious about titrations, which would also be totally cool. So, speaking of, it looks at first glance like we only have 2 problems to work through, but we actually have 10 problems, and we're going to try to do them all in the next hour. It's ambitious, but I like being ambitious if possible. So, both of these are titration scenarios. In our first question, we're titrating a strong base into a weak acid, and they want to know what the pH is after titrating these 4 different volumes of the strong base into that volume of that weak acid, formic acid. And in our other scenario, we're actually dripping a strong acid into a weak base. And most of these questions, they want to know the pH, but a couple of them, they want to know the volume at particular times. So let's look at that one second and the first one first. And let's set up our problem before we dive into it, or our 4-part problem, which is a little visual representation of what this question is asking. So we have, do my best with nice symmetrical coherent drawing. We have a burette, little drippy glass tube with a bunch of volume demarcations. There's a stopcock here that we can turn and very carefully control how much and at what rate the liquid inside the burette drips out. And the liquid inside the burette is our sodium hydroxide, strong base, and we are told in this problem that the concentration of sodium hydroxide, so it's an aqueous solution, so it's in there with water, and it's at that molarity, right, or that many moles per liter. And we're going to be dripping 0 liters, and then we're going to be dripping that many liters, 0.015, that's 15 milliliters, 25 milliliters, and then finally 30 milliliters. And I say dripping, but dripping into what? We will be dripping it into a flask of some sort. Kind of a weird looking flask, that's alright. And this flask contains formic acid. And it contains a quantity that we are told is 50 milliliters. Or that many. liters. And we are told that it is at a concentration of 0.1 molar. So let's say the formic acid is green, which I'm assuming it's not actually green, but there's some green formic acid there. We're dripping in some blue NaOH, and we will be calculating the pH at these 4 different volumes of introduced sodium hydroxide. Of course, we have the answers already, and that's great because we're going to do the calculations and we'll immediately know if we did them correctly. Well, and I'll extra know because I did these all last night for practice and to make sure I knew what I was doing. So I'm pretty confident we're going to get these answers. Uh, Really quickly, it would always bear mention to talk about how these two substances will dissociate. So sodium hydroxide, once it's in water or any sort of solution, let's say you had a solid sodium hydroxide salt, of course it's going to dissociate into aqueous sodium cation and aqueous hydroxide anion. And the sodium cation is a spectator that we basically don't care about. It is very happy to not take or give any electrons or protons. It's a neutral spectator. So really what we're talking about is the hydroxide. When we talk about sodium hydroxide, the strong base, we're really talking about the hydroxide part. So before we drip any of that, though, into the formic acid, which, in case you're curious, formic acid looks like this. And we're going to call that H form. Pardon me. And when it is in water, which it currently is, this is a aqueous solution. Formic acid likes to basically give this here proton to that there oxygen, creating H3O plus, which is the thing that gives solution its pH. That is the H of pH. So the formic acid, the H form, is going to give that proton to the water, which means that it will leave behind most of itself, except for that with a negative charge there, as what we will be calling form minus, which is also known as formate. So we're not going to get bogged down in the details, but I think it's important to just talk about what's going on here if you really want to answer these questions. So before we've added any base, the only thing that is influencing the pH of the solution is the H form. I'm going to write this one more time, which upon combining with water will create hydronium ion and formate. And if we wanted to find stuff out about the pH later, a rice table based on this equation would be exactly the thing that we need. Now, one issue that you might be predicting is we don't know one critical piece of information about formic acid yet. But let's come to that in a sec and just talk about what we do know. So that's our reaction. Our initial concentrations of all these things, let's just say that somehow we had prevented ionizing from occurring. Our initial concentrations of our hydronium and formate would be 0. If somehow we had formic acid, where just like I drew it right here, in green, where you had made sure, like maybe you stored it in another acid that was really strong or something, and you made sure that that proton stayed on. But then you suddenly permitted it to interact with water and to, oops, kind of weird that those are green, but so be it. You suddenly permit it to, and then it has a change. It goes from its initial 0.100 molar and has a change where it loses some amount that we don't know what it is. Some amount of the moles that are in there and some portion of the concentration disappear, but we don't know what it is. But whatever it is, it disappears from the formate, and that exact amount is gained by the total concentration of hydronium. And that exact amount is gained by the total concentration of formate, because that's what happens when H form falls apart. It becomes H3O plus and form minus. And this whole time, there's just so much water in here that we do not factor it in. It's a liquid. It's the solvent. It does not factor in. Why? That's for another video. So after that change happens, we reach eventually an equilibrium. Because keep in mind, this is going back and forth. H form is becoming form minus, but then some other H3O plus comes along and gives its extra proton back to the form minus, which becomes H form again, and so on and so forth. And it goes back and forth until eventually we reach these equilibrium concentrations. And this is where our equilibrium uh, acid dissociation ratio comes into play, which is something that is experimentally determined. And it is the mass action expression of our products over reactants. If we had stoichiometric ratios, we would incorporate them now, but we currently don't. So again, this is our products over reactants. And when it reaches equilibrium, according to experimental data, any given acid will have a ratio of concentrations that it settles in. Now, we're going to have to obtain that ratio from some sort of literature source. Oops, I had to spell that. And I was going to spell and abbreviate it wrong. We're going to use Appendix H of the OpenStax book, or hopefully any source that you want, because a Ka value should be a universal constant when we're talking about, standard conditions, ostensibly 25 degrees Celsius and 1 atmosphere of pressure and stuff. I'm sure if you mess with those, you could change your Ka values. But from Appendix H of our book for formic acid, or again, from hopefully any source, the Ka of formic acid, which I'll write in both ways, is 1.8 times 10 to the minus fourth. So we can plug that into that, and then plug the values from our equilibrium row into the broader expression, and then we can solve for x, which means we will have solved for the concentration of hydronium. Oh, and of course, it bears mention that if we're seeking pH, we find pH by taking the negative log, base 10, of the concentration of hydronium. At any given time, whatever the concentration, which of course is quantity divided by volume, which in chemistry typically is moles per liter, the negative log of the concentration of hydronium will give us the pH, and based on this Rice table, the concentration of hydronium will be X. So the pH should be the negative log of whatever X we can solve for by using the expression we set up, the information we have, and this Ka that we had to look up. Or if we didn't have an Appendix H available to us, we'd have to do a bunch of calibration experiments and establish a dissociation curve And then from there, I guess we could come up with our own experimental Ka and use that. However, we can stand on the shoulders of giants and just use the Ka that we're given. So 1.8 times 10 to the minus 4, and now I'm just copying essentially this expression right here, but inserting the values from the E row of the rice table, the equilibrium row, and from the Ka value as obtained from Appendix H. And that's X is the concentration of hydronium, right there. And the concentration of formate, also X. And the concentration of formic acid, so we started out with this much, and then we lost some, right? So we started out with that concentration, and then we lost however much we lost. And you might be looking at this right here and thinking, yay, a quadratic equation. Or you might be thinking some other thought that is less celebratory, perhaps. The good news is most of the time we don't even have to do the quadratic equation to get a reasonable answer. You also might be thinking to yourself this instead, is x small? Because if x is small, what we can do is keep these x's around since they're being multiplied by each other, which is going to have a big effect. But we can get rid of this x if x is small. Because if this x is so much smaller than this number, this concentration, that was the initial concentration of formic acid, if the x is way smaller than that, then it basically won't matter if we subtract it from that. If x is substantial enough, then it might matter and it could make a big difference. So the guideline for testing, if x is small, of course, the test is your initial concentration of your weak acid divided by the Ka of that weak acid. The Ka of that weak acid, as sort of shown by this expression, indicates how much it will ionize, how much it will dissociate and fall apart and create hydronium, which is essentially acidity. So the Ka, the bigger the Ka, the more it does that, the more acidic it is, the stronger the acid. The stronger the weak acid, but the stronger the weak acid. So if the Ka is big, then the X's small test will probably fail. Because the X's small test needs this ratio to be greater than 400. So if the Ka is big, then you get a lot of acid, and X is not small, and this is going to mean something. But I happen to know that in this case, if you divide, and you could find this out very easily using calculator, the given initial concentration of our weak acid, which was that, right? That's our concentration H form given in the question, and we divide that by the Ka that was obtained from the table. Then it equals, according to the calculator, 555.5 forever, which is not like way bigger than 400, but bigger than 400. So yes, X is small. And I know this is a lot of setup on this question, but that's just the way it goes. Maybe we'll jump around on some of these. So, based on x being small, we can say that that x in the denominator doesn't really matter. So, we now have this expression, and if we're going to solve for x, which again will be the hydronium concentration, then we're going to get this. And then to solve for x, all we have to do is take the square root of those. And we'll get x, which will equal the hydronium, which means we just take the negative log of that, and we will have the pH. And in this case, I have already done these calculations, and I'm going to just keep blazing through this so we can hopefully answer some significant number of these questions. I'm already like 19 minutes into the stream, apparently. And I still haven't quite answered this first question, but we've set it up to answer the next few. Hopefully really quickly. So when you put this in your calculator, it turns out that you get the square root of 1.8 times 10 to the minus 4th times 0.1 is this, basically. And the negative log of that is 2.37, which is what the answer key says. So yay, we got it. All right, let's now finally look at the next part. And I think I might, for now, I'm going to make all this stuff small, basically. Let's just, we can leave, oh yeah, we'll leave that. Try to leave that. Hopefully I left that. Let's see. All right, that actually worked surprisingly well. Thank you for your service. Okay, so now we're going to actually drip 15 milliliters of sodium hydroxide in there. And again, we're just going to say that whatever sodium hydroxide goes in there, it's essentially hydroxide. And here's what's going to happen when that happens. There is going to be some H form sitting around. Of course, we just calculated that some of the H form becomes form minus, the form 8, but a lot of it doesn't, right? The Ka, again, was 1.8 times 10 to the minus 4th, which is not a big number. That's this. So that is representative of the ratio of how much of the formic acid actually loses its proton. So a lot doesn't, okay? So we have this formic acid sitting around in the flask, and when that OH minus drops down, this is basically going to happen every single time. The OH minus has this lone pair over here that would just love to get that proton, because when it does, it gets to become H2O. Neutral, no charge, super happy, it's water, and then that creates form minus. So the formic acid, the H form, was already creating some form minus on its own, but when we introduce the strong base sodium hydroxide, we're going to create a heck of a lot more. So if we introduce 15 milliliters of sodium hydroxide, that's that many liters, and we've been told that the concentration of this sodium hydroxide is 0.2 moles per liter. That means that we're introducing 0.030 moles. I mean, that seems like I did that right. That seems, there we go. I knew it seemed too good to be true. I missed a decimal place. Let me correct that. See, it wasn't times 2, it was times 0.2, which means we have to move the 3 back a decimal. So when we drip in our 15 milliliters, part B, 15 milliliters, when we drip in the 15 milliliters of 2 molar NaOH, we're introducing essentially this many moles of OH minus. And OH minus hydroxide is so basic and so good at taking protons, and formic acid is pretty good at giving away protons, that we're going to essentially assume that all of the OH minus is going to take a proton from the formic acid, from the H form, meaning that all of that OH minus that drips in becomes H2O and consumes the H form. So how much H form did we start with? I'm very bad at managing my font sizes here. We have 50 milliliters, and it's 0.1 molar, right? So this was sodium hydroxide right here. Let me change the color just to make this obvious. For our H form, we had 50 milliliters, and the concentration is 1 molar, 0.1 mole per liter. I think I forgot to say points a second ago. That's parenthetical. And that, of course, gives us this. So if we are introducing 0.003 moles of OH minus, and every single mole of OH minus will consume as much H form as it can. That means we're going to leave behind that much formic acid. And in doing so, the byproducts here, we're going to get water. When the OH minus, the hydroxide, takes the proton, that's just going to create water. The formic acid, the H form that's consumed by that hydroxide, will now be formate. And then we're going to have 0.002 moles of H form remaining. And that is what's going to be responsible for the pH. So is X small? Let's see. X small test. 0.02 divided by 1.8 times 10 to the minus fourth. I mean, yeah, X should be even smaller. That should be even smaller than last time, because last time... oh, wait, but that's not the concentration, is it? My bad. That's just the moles. We actually have to take those moles. Basically, I'm sure X is small, but we're going to do it just this one last time anyway. So we really have 2 moles, but we started out with 50 milliliters, and then we just put in 15 milliliters of aqueous solution. So that's actually, of course, 65 milliliters. And let me just verify what this ratio is. So 0.002 divided by 0.065. Okay, so 0.0307. I mean, X is still small, but let's actually solve it and not just take it for granted for a moment. But soon we will take it for granted. All that T, because I need a letter. Oh, maybe X is not small anymore. Did I do that wrong? 1, 2, 3, 4. X is not small anymore. But you know what we can do? And you know what we're going to do? This, and this is what I thought of yesterday and forgot to think of until right now. But this is what we're going to do. This is a classic case where we have, of course, our H form. We have 0.002 moles remaining of H form. And we have formate. And all of the sodium hydroxide consumed some of the H form, right? All of the hydroxide consumed some of the H form to create that exactly equivalent amount of formate. Concentration, I should say. So, in our flask, after introducing that much sodium hydroxide, we have a formic acid and formate buffer system which is the perfect time to use the Henderson-Hasselbalch equation. Because we have, this is the A minus, right? That's our concentration of base, essentially. Here's our concentration of acid. So we're basically ready to rock some Henderson-Hasselbalch here. So the pH is going to equal the negative log of the Ka, which we're talking about all of this in the context of formic acid, so that's our Ka, plus the log of the ratio of the newly created conjugate base divided by, sorry, it's not a ratio divided by, it's the ratio of the newly created conjugate base and the remaining acid. So once again, that's A minus over HA. That's what that is right there. And if we begin to do this on math a little bit, turns out that the negative log of this and the log of that ratio equals 3.735 plus, sorry, it was 0.176, which equals pH after 15 mils of NaOH molar. That pH equals 3.92. I got a little sloppy with sig figs, but as long as we're getting like within a hundredth or so, a couple hundredths, we're probably good. So there we go, and this makes sense because before we added any base, this solution initially was, oh, where did it go? I made it all small, it went away. Our initial pH, right here, that's quite acidic, right? The closer to 0 it is, the more acidic it is. And now that we added a, fairly good portion of base, our pH has gone up. It's still quite acidic. It's still less than 4, still quite acidic. This is still a solution of formic acid, but it's also a buffer with a weak acid and its conjugate base. Still an acidic buffer, but it has become less acidic. So now we're going to introduce 25 milliliters. Okay, I'm not going to minimize that yet. I'm going to keep scrolling down. Okay, so part C. We're now introducing 25 milliliters of our 0.2 molar NaOH. So as far as the resultant, I'm going to kind of try to gallop fast here. See if we can come even close to finishing all of these. Oh, that's liters right there. And again, the fact that we're talking about the tenths place here means that we're going to just move everything back 1 decimal place in addition to multiplying by 2. And that means that when we add 25 milliliters of NaOH at this concentration, it means we're adding this many moles. We're adding 0.005 moles. If you recall, we initially started with 50 milliliters. This is our NaOH. And here's our H form. That initial 50 milliliters of 0.1 mole H form meant that we started with that many moles. Oh my gosh, that's the same number. And again, we don't really care about the Na. It's just OH minus, and here's H form. It's the same number. They cancel out. It will be fully consumed. So when you add exactly 25 milliliters in this scenario, we're consuming exactly, not more, not less, exactly all of the formic acid. So we will have no OH minus and no formic acid at that point. So what will we have? What we will have is that all of that will have become conjugate base, formate, form minus, right? Every single last molecule of H form will have had its proton taken by water. So we're going to get that same amount of new water in addition to whatever water was there. And it's going to leave behind that much formate. So this is a base. So now the pH of our solution actually really depends on how good is this at being a base. So form minus, the equation for form minus being a base is that it sees some water, or anything with a proton, but let's do water, and it takes it, and it becomes H form once again, and it leaves behind an OH minus. And it will do that to some extent, but it's a weak, weak base. Like, formic acid is a strong-ish weak acid. I guess probably strong, medium strong. Formates is quite not strong. That's how it always works. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So also, as we're talking about a balanced chemical equation about the behavior of a base, we actually need our Kb value, which is the exact same concept as Ka, except it talks about hydroxide and the product is conjugate acid. And the reactant is the base, the conjugate base. Now, you might be looking in your appendix H or your appendix I, but you probably won't find the Kb of formate because it's much more convenient and practical to give you the Ka of formic acid, but we can convert back and forth between Ka and Kb by using Kw. This is, of course, the auto ionization. Sorry, I should have this backwards over here too. The auto ionization of water, where water just it acts as an acid and a base unto itself. And the experimental extent to which that happens is 10 to the minus 14. Like if you take the concentration of this times the concentration of that at 25 degrees Celsius, oops, in 1 atmosphere, then each of those will be 10 to the minus 7 moles per liter. And when you look at the concentration of both those ions, it's 10 to the minus 14 moles per liter. This also means that if we know the Ka, we know the Kw, which we do because Kw is this, then you can calculate the Kb of the conjugate base, which is what we're going to do. So the Kb of the conjugate base, which we need to solve this, is Kw over Ka of H form, which is 1 times 10 to the minus 14 over 1.8 times 10 to the minus 4, which is, I think I remember what this is, but I'm going to double check here. Yep, a very small number, 5.5 forever, times 10 to the minus 11, right? So that's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 5's forever. Very small number. So I basically can guarantee you x is small. Is x small? Well, I can basically guarantee you, but of course, since we're talking in base here, x is small is going to basically be our concentration of formate over our concentration, over our Kb. We have Kb. Kb is tiny, so probably this is going to be a huge number, but we should figure out our concentration of formate. We know that we're going to have that many moles of formate after adding the 25 milliliters of sodium hydroxide, but we need to divide it by the new volume. And we had started with an aqueous solution of 50 milliliters, so that's of course 0.05 liters. And then we added 25 milliliters, liter, mole, cool, form minus, cool. And so that turns into that many moles per liter. And you divide that out and you get, and sixes forever. So we have basically right here, this same thing is like 6 times 10 to the minus 3 forever, 5 times 10 to the minus 11. And if you do that math, it's like 1.2 times 10 to the 12th or the ninth or something. And yeah, that one is our classic, way bigger than 400. So yes, x is small. So we can basically do the exact same thing as last time to get the pH, because this is just, for this moment, this is simply a solution of formate. So the thing is, this X, since we're talking about base, it's the concentration of hydroxide, not hydronium. We just have to keep that in mind. So the concentration of hydronium here, this is the same thing we did in the first part, except for, again, we're talking Kb instead of Ka. So 5.5 times 10 to the minus 11 times, our concentration was this right here, right? That's our concentration. And you do that math in your calculator, and you're careful about parentheses and everything. 1.92 times 10 to the minus 6 equals x equals concentration of hydroxide. So now if we negative log that, we will have our POH. So OH equals the negative log of 1.92 times 10 to the minus 6, which equals 5.716 or so. And of course, pH equals 14 minus POH. So therefore, pH 14 minus this 5.716 equals 8.28. So that's when we've added exactly enough of the NaOH to consume all of the formic acid and render exactly all of it into the conjugate base formate. Okay, let's do another one. Slash the last one. So now we're just pushing a little bit ahead and we're adding an additional 5 milliliters for a total of 30. Because let's look at it like this. So we're adding 30 mils of NaOH. And okay, well, we're at least going to get through this one problem. I don't know if we're going to get very far on the other problem, but we'll at least get through this one. So 30 mils of NaOH is going to be 30 mils times, we're told that it is 2 moles, 0.2 moles per liter. So that's going to equal 0.006 moles of OH minus that we're introducing. And of course, every time we're doing these, we're taking it back to the beginning and just looking at it as an entire titration. We initially had that many moles of formic acid, and when we introduce this much sodium hydroxide, all of that is going to be consumed and become formate. And again, this is moles right now. I haven't turned it into concentration at the moment. And that's going to leave us that much 0.001 moles of excess sodium hydroxide. And in the interest of time, I'm not going to show you why, but the amount of hydroxide that would come from that is negligible. It's like, or something like that. I calculated it last night. But the hydroxide from the sodium hydroxide excess is right there. So it's like way negligible to consider the extra hydroxide from here. So for all practical intents and purposes, we're going to ignore it and say that this excess hydroxide right here is what's really going to determine the pH. And that's like actually kind of a lot because we have 80 total milliliters now because we had 50 and 30, right? So when you divide 0.001 moles by 0.08 liters, you get this molarity. That's the molarity of hydroxide, and the negative log of that is, where to go? There we go. The negative log of that is 1.9. Negative log base 10. And that's the POH. So the pH equals 14 minus the POH, which equals 12.1. And that super makes sense because now we have hydroxide, strong base, fairly small amount of liquid. 80 milliliters is not a lot. It's a fairly big amount of hydroxide in a way. Usually in a lab, you're not dealing with full moles of stuff. I mean, I guess case by case. I retract that because who knows. But that's quite basic. And that totally makes sense. Okay, we at least have time to start the next one. But those are the 4 answers for that first part. So we can be happy that we even got that far, right? I'm just going to move this stuff out of my way. Come back to it later, possibly. I get everything. Ooh, missed it. I don't believe there is anybody here. If there were, I would say. Well, I guess I am going to say it even though there's not anybody here. Do you have any questions? I suppose if you have questions, then you'll have to ask them in the future from the moment that I'm saying this. And I don't know if you'll be able to ask them to me. Maybe. But there we go. Oh, come on. All right, I'm just going to give up this if this part fails right here one more time. So I think, to me, the big take-home message with everything that just happened, all right, we're just going to move this below everything else. The big take-home message is this stuff is not that bad. You just have to be careful. There are many opportunities to confuse which number meant what or how many decimal places something had, and that'll throw you way off. So as long as you're careful, you're good. Okay, so this scenario is very similar to our last one. The only big fundamental difference maybe is that we're dripping into our weak base, NH3, and we're given that that is the KB. So again, what is a KB? It's when NH3, with this little lone pair over here, sees some water, like, hey, water. And of course, this goes back and forth a little bit, but it's like, hey, water, give me your proton. I just drew that weird kind of accidentally, but that's NH4, right? Uh, and it also creates an OH minus in the water. So that's the KB expression. And again, KB is going to be at equilibrium, the concentration of OH minus NH4 plus ammonium over the remaining concentration of ammonia. And so we'll just have to keep in mind that everything we're talking about right now for this part is going to be OH. If we want to talk pH, then we're just going to have to subtract it from 14. So is x small? That's pretty big. That's really small. Basically, yes, I'm not even going to test it. I'm just telling you it is. Please double check me on that. But that means that x, which is concentration of OH, is going to be that same thing that we've been looking at. It's going to be Kb times uh, concentration of ammonia to start. That's the same thing as form minus in that last problem. So that is square root of 1.8 times 10 to the minus fifth times 0.6, and that equals 3.28 times 10 to the minus third. And so the negative log of that equals 2.48. But that is not the pH, that's the pOH. The pH equals 14 minus that, which equals 11.5, which makes sense. That's pretty basic. Ammonia is pretty basic. It's a weak base, but it's a strong weak base. So that is our initial pH before we have titrated in anything. What are we even titrating? Sorry, I forgot to mention that earlier. It's actually probably better that way. Here's our burette, here's our stopcock, volumes are demarcations, and we have HCl, strong acid. Of course, HCl in solution just completely goes to H and Cl. And presuming that it's an aqueous solution, those H's, those H pluses, find a water and become H3O plus. And chlorine, just like sodium before, is a spectator that we don't care about because it's just so happy and it's not going to mess with anybody. So what volume of acid in milliliters is needed to reach the equivalence point? So the equivalence point is like we had in our previous problem when we added the exact, this was the equivalence point right here, right? When we added that amount of hydroxide to consume that exact amount of starting formic acid. So now it's asking exactly how much of this hydrochloric acid. So the hydrochloric acid is 1 molar, so that's going to make it pretty easy. Let's figure out how many moles we even have of the starting ammonia. So we are talking 90 milliliters. So for our ammonia, we have 90, do that correctly, 90 milliliters. And the ammonia is 0.6 moles per liter. So how many moles of ammonia do we start with? So looks like we start with 0.054 moles of ammonia. So how many milliliters does it take? Well, for every one, when's this better? This is the convenient thing about something being 1 molar, is for every 1 milliliter of something that's 1 molar, you get that same number of moles. So we basically need 54 milliliters of 1 molar HCl in order to consume exactly 0.054 moles of NH3. If we have 0.054 milliliters of HCl, then we're going to get that many moles of the H plus, which the lone pair on that ammonia is going to see that H plus and just grab it, and it's going to make NH4. All of it, exactly all of it. So we're actually going to have exactly 0.054 moles of NH4. And from there, we we'll have consumed all of that, and we'll have consumed this. So we're basically going to have a small amount, I mean, not that small. We'll have an amount of this very weak acid, the conjugate acid, and I guess we should find the Ka of it. Maybe we could do it a slightly different way, but I think the way that makes sense at this moment for me to do this is, oh, that wasn't even the question. It just said how much. Right. Okay, so we answered it already. I think we started answering a later part of it, but it's that many liters, or 54 milliliters, is the answer for that part. And what is the volume needed to reach the halfway point? So we're actually maybe going to get very close to the end of this. So to reach the halfway point, where if we're starting with, so that was what, C? That was B. This is B. Okay. Got A right here. This part was B. Here's C. Answer to A. Answer to B. For C, we're talking about the halfway point. Halfway to equivalency. So we had this many moles to start, and when we consume half of those, that's the halfway point. So half of 54 is 27. So if we consume, that's our ammonia, we consume half of it, then we're going to have half of it left over. And half of it will have become the conjugate acid, ammonium. And our Henderson-Hasselbalch goes a little something like base over acid, which in this case wouldn't even matter, because as you can see, that equals the pKa plus the log of 1, which equals the pKa plus 0, which equals the pKa. The pH equals the pKa at the halfway point. That's how this always works. And it looks like it would take how many moles of HCl? Exactly 0.027. And since this is 1 molar HCl, that's 27 milliliters. So we need that many moles of HCl, and that's going to be 27 milliliters of our one, that's a 1, I swear, of our 1 molar HCl. Okay, awesome. So question D, what is the pH after we've added 50 milliliters? Okay. So 54 cancels it all. But if we add 50 milliliters, then we're basically going to have that many liters, or sorry, moles of our ammonium left, right? I'm just skipping a lot because I want you to see, like, we put in 50.050 moles of HCl. It will consume most of that ammonium and leave that much behind, right? Okay, so the POH from there, X is definitely small. We're told the KB already. The POH from there is going to be, oh, except this would be a Henderson-Hasselbalch, right? Yeah, sorry, my bad. This is Henderson-Hasselbalch because we do have that NH4. So now our pH is going to equal the, well, I'm actually going to, since we're talking in base, and that's what I know, I'm going to say the pK8, the POH equals the pKb, which we have, plus the log of the ratio, no, since it's always products over reactants, we're now talking about a base dissociation. It's going to be like that. But we're just going to subtract this from 14 later. So the POH is going to be the negative log of 1.8 times 10 to the minus fifth. That was our given pKb, or you would have found it somewhere, plus the log of, so once the hydrochloric acid has consumed most of our ammonia, we're going to have that much NH4, right? And we're going to have this much of our NH3 remaining. Now, I've left out concentrations here because they have the same volume. So if we speak in concentrations, that would still work, but the volumes would cancel out. So I'm just working straight up in moles. Doesn't really matter either way because it's a ratio of the same units, right? I mean, it's different species, but the units cancel. The ratio itself is what matters. So the POH is going to equal the negative log of that is 4.745, and that ratio of essentially 50 divided by 4 equals 12.5. So, plus the log of 12.5, which is going to equal the 4.75 right there. I just rounded a digit. Something crazy like that. .84 equals the POH. So the pH is 14 minus that. Which equals 8.158. And that totally makes sense because even though we started out with a much more basic, right, our first answer here was this 11.5. That's when it was just ammonia, but now we've consumed a lot of that ammonia and converted a lot of it into ammonium NH4+, but it's still basic. There's still some ammonia there, and ammonia is much better at being a base than ammonium is at being an acid. They're both weak, but this is a better base than this, which is a worse acid. So it makes sense our solution is still a bit basic, right? A bit alkaline. Okay, so technically we are done with the live stream as far as the scheduled time. It looks like there are two more questions, E and F. But I think what I'm going to do is come back and make another video where I clean up some of the questions I didn't finish, maybe correct any mistakes I catch when I review these, maybe go over some concepts some more. But yeah, thank you for watching this. I hope that you had fun working with acid-base pH titration type stuff. And yeah, stay hydrated. All right.